So we last left off in balancing redox reactions. So now that you've seen examples of balancing redox reactions under acidic and basic conditions, I'd like you to start off by attempting to balance the following redox reaction under basic conditions only. So start from the ground up, and you're more than welcome to message me your proposed half reactions or your proposed identification of the oxidizing and reducing agent. We'll spend about 5 minutes working on this problem, and then we'll come together as a group to discuss and review. Really want to make sure you're getting this hands-on practice so that way you're comfortable balancing redox reactions. You will see at least one redox reaction balancing equation on your final and on exam 3. And don't be shy to message in the chat any questions you have or any proposed half reactions that you've generated so far. And we'll discuss in about 2 to 3 more minutes. And we'll discuss in about 1 more minute. And don't be shy to propose and post your balanced redox reactions. If not, we'll work together as a group and go through this problem in about 30 more seconds. Okay, so let's discuss this problem. So first I'm going to rewrite my equation. Okay, now let's assign oxidation numbers. So what is the oxidation number of chromium in chromium 3 oxide? What's the oxidation number of chromium? And don't be shy to type in the chat. +3, yep. Okay, oxygen's oxidation number is -2. Would someone like to volunteer? When you calculated the oxidation number of chlorine in hypochlorite, what oxidation number did you get? We've actually seen hypochlorite before, but let's propose, what is the oxidation number of chlorine in hypochlorite? And to help everyone along with this, let's use our oxidation number equation. So the oxidation number is our total charge, which is -1, minus the oxidation number of oxygen, which is -2, times the number of oxygen atoms over the number of chlorine atoms, which gives us an oxidation number of +1 for chlorine. Does that make sense to everyone so far? Okay, so let's do the same thing for chromate. The oxidation number of oxygen is -2. Would someone like to take a moment and calculate the oxidation number for chromium and propose their oxidation number for chromium in the chat? +6, exactly right. We get this by taking the total charge minus the oxidation number of oxygen times the number of oxygens over the number of chromium atoms. And now for an easy one, what is the oxidation number of chloride? What's the oxidation number of chloride? -1. Okay, let's look at our oxidation half reaction. So for our oxidation half reaction, we are losing electrons. Our oxidation number is going up. What species, what atom is being oxidized in this case? What atom is being oxidized? What atom is being oxidized? Chromium, exactly right. Now, before we do anything fancy, do we have the same number of chromium atoms on each side? Do we have the same number of chromium atoms on each side? No. So how many chromium atoms do we need on the right? How many chromium atoms do we need on the right? 2. Yep. Perfect. Okay. Now, looking at our electron balancing, how many electrons do we lose for chromium when we go from +3 to +6? How many electrons per chromium atom? How many electrons do we lose per chromium atom? 3. And we have 2 atoms, so that gives us 6 electrons. So how many electrons do we lose? And where do we put those 6 electrons? On the left or the right? Do we put those 6 electrons on the left or the right? The right, yep. Okay, so let's now rewrite this equation because there's still more work to be done on this equation. Okay, so now as we notice, we have 8 oxygens on the left and 3 oxygens on the right. So if we're balancing oxygen under basic conditions, we know that if we want to add 1 oxygen to the left, we use the following pair: 2 hydroxides on the left, 1 water on the right. So if we need to add 5 oxygens to the left, we just multiply this expression by 5. And that in turn gives us Cr2O3 plus 10 hydroxide leads to 2 CrO4 2 minus plus 5 H2O plus 6 electrons. Now just take a quick moment to appreciate this equation, and I'd like you to just check really quickly, is this equation balanced in terms of hydrogen and oxygen? Did we successfully balance hydrogen and oxygen? Is this equation balanced? Let's just try to answer that question. Did we balance it? Okay, so checking this equation is balanced in terms of atoms. So let's now look at our reduction reaction. Let's look at our reduction half reaction where we are gaining electrons. So looking at our equation, what atom is gaining electrons? What atom is gaining electrons? Chlorine. Okay, so let's write that out. So we have hypochlorite going to chloride. So we're going from +1 to -1. So how many electrons have we gained? How many electrons have we gained? When we go from +1 to -1, we've gained, of course, 2 electrons. Okay, now I'm going to rewrite this equation as there's still more work to be done. Is this equation balanced in terms of oxygen atoms? Do we need to balance our oxygen atom? Do we need to balance our oxygen atoms? Yes. So if I need to add 1 oxygen to the right, I use the following pair. H2O leads to 2OH. So I'm going to add water to the left, and I'm going to add 2 hydroxides to the right. And that in turn gives me the following equation. So we have 2 electrons plus hypochlorite plus water leads to chloride plus 2 hydroxide. I'm now going to rewrite my oxidation half reaction. Okay, and what's the least common multiple between 2 electrons and 6 electrons? What's the least common multiple between 2 electrons and 6 electrons? What's our least common multiple? What's the smallest? So what times 2 would give us 6? What times 2 would give us 6? 3. Okay, so if we add our equations together, we have 6 electrons plus 3 per hypochlorite plus 3 water plus chromium 3 oxide plus 10 hydroxide leads to 3 chloride plus 6 hydroxide plus 5 water plus 6 electrons plus 2 chromate. Now we cancel equivalent species on each side. We have the same number of electrons on each side. And then finally, we write out our balanced chemical equation. Here we go. Although it took a fair number of steps, the only thing that's new is that when we balance under basic conditions, we add water and hydroxide pairs. Does this example make sense to everyone? Is everyone comfortable with what we just did? Any questions on the following example? Okay, so I have a few more examples for you to work on at home. So I'll leave that page as an example for you to work on at home. I would recommend that you do. Now what we're going to do is we're going to look at some reactions that can be redox reactions, and we'll note, and we're going to talk next about different classes of reactions. So a decomposition reaction is the reaction of a compound to give one or more elements or compounds. So for example, carbonate salts commonly decompose to yield a metal oxide and carbon dioxide. So for example, in this case, calcium carbonate, when heated, decomposes to yield carbon dioxide and calcium oxide. Let's look at another example. If we have sodium carbonate and we heat sodium carbonate, what products would we expect to observe? What products would we expect to observe? And don't be shy to type in the chat. What products would we expect to observe? Carbon dioxide, yep. And what is our other product after carbon dioxide? What's our other product from this reaction? So metal carbonates decompose to yield carbon dioxide and a metal oxide. Remembering that sodium has a +1 charge and oxygen has a 2-, we cross our charges and we get sodium oxide, which is Na2O. So just make sure your formulas are balanced with respect to charge. Perfect. So binary ionic compounds can also decompose to their component elements if they are heated. So an example of this would be mercury oxide decomposing to mercury and oxygen. Another example would be sodium chloride. And what would sodium chloride decompose to if we heated sodium chloride? What would sodium chloride decompose to? What are the component elements in sodium chloride? What will sodium chloride decompose to? What are the component elements in sodium chloride? Sodium, yep. Okay. And what is the elemental form of chlorine? What is the formula of elemental chlorine? Cl2. Exactly. Now we just balance our atoms and our equation is balanced. Okay, perfect. So hydroxides, as we observed in the copper lab, decompose to yield a metal oxide and water. So let's look at a slightly tricky example. So if we have aluminum hydroxide and we heat our aluminum hydroxide, what products will we generate? What products will we generate as this hydroxide decomposes? What products will we generate? Yep, aluminum oxide, which is Al2O3. And what's our other product going to be? Water, exactly right. Now to balance our equation, first we balance aluminum and then we balance hydrogen. Perfect. So I just want you, when we go and overview these different types of reactions, to be able to classify reactions as decomposition, acid-base combination, etc. And to do that, we just look and see we're going from one compound and generating two or more new elements or compounds. Another decomposition reaction that is often seen extensively in preparatory chemistry courses is the decomposition of chlorates. So chlorates, which are salts containing chlorate, which is ClO3 minus, they decompose to yield a metal chloride and oxygen gas. So for example, potassium chlorate decomposes to yield potassium chloride and oxygen gas. This reaction is in fact a redox reaction. How do we know this? Well, if we look at the oxidation number of oxygen, we're going from -2 to 0, and chlorine is going from, let's see, +5 to -1. One interesting thing you can do if you want to practice balancing redox reactions is to look at all these different types of reactions and try, whenever you see a redox reaction, try balancing it from scratch. So another common decomposition reaction that we saw involves carbonic acid. So carbonic acid decomposes to water and carbon dioxide. Standard fare. Okay, let's look now at a combination or synthesis reaction. So it's the exact reverse of a decomposition reaction. In a combination or synthesis reaction, we have two or more elements and or compounds reacting to give a single compound. So for example, if you combine a metal and a nonmetal, you generate an ionic compound. So for example, if you mix aluminum and bromine, you get aluminum bromide. If you mix, for example, zinc solid and you treat it with chlorine gas, what product would we expect to observe from this combination reaction? What product would we expect to observe from this combination reaction? And don't be shy to propose the products in the chat. So our metal and nonmetal are combining to form an ionic compound, which would be zinc chloride. Okay, let's look at another combination reaction. So a metal oxide and water will combine to form a metal hydroxide base. This is why metal oxides are sometimes viewed as basic salts. So for example, magnesium hydroxide and water react, magnesium oxide and water react to yield magnesium hydroxide. By the same token, if we have sodium oxide solid and we place sodium oxide in water, what product would we generate? If we place sodium oxide in water, what product would we generate? Sodium hydroxide, exactly right. Remember that your equations need to be charge balanced, so we'd make two sodium hydroxide molecules. Because sodium has a +1 charge, hydroxide has a -1 charge, we cross our charges. Okay, let's keep going. Oops, one moment. So Non-metal oxides are typically considered quote unquote acidic because non-metal oxides and water will combine to form an acid. For example, carbon dioxide, if it's allowed to mix with water, will form carbonic acid. This is why you often had to boil water in the laboratory to drive off and minimize the amount of dissolved carbon dioxide. By the same token, sulfur trioxide gas is quite dangerous to work with because it generates what acid in water? Would someone like to propose a formula for the acid generated from sulfur trioxide? It's quite a famous acid. Sulfuric acid, exactly right. Exactly right. So that's why sulfur trioxide is dangerous, because if inhaled, it reacts with water in the lungs and makes a strong acid, causing irritation. There are also other miscellaneous combination reactions that you'll see. When you think combination, think multiple compounds combining together to generate one product. So exchange reactions are another class of chemical reaction. It's a reaction where atoms in two or more different compounds are exchanged to give two new compounds. So for example, A, B, and C, D, we exchange two of our atoms to yield two new products. So this is often observed via exchanging the cations or anions in ionic compounds. So just like when we discussed predicting the products from precipitation reactions, when we discussed precipitation reactions, quite simply, I told you to take your cations and swap them and see whether an insoluble product is generated. This precipitation reactions fundamentally are exchange reactions. We are exchanging our participating atoms or ions to yield two new products. Okay. So a single displacement reaction, so displacement is the name, it is implying an element is reacting with a compound to give a new compound and a new free element. So these displacement reactions can be classified into a few major categories. The first of which is known as the hydrogen displacement, where a displacement produces hydrogen gas. So a metal reacts with water to give a base and hydrogen gas. So if we look at our metal in detail, we notice that we've gone from a metal and water to a metal hydroxide and hydrogen gas. Allow me one moment to reset OneNote. Okay, so focusing next on looking at this displacement reaction, we can see that our metal has in effect replaced or displaced one of our hydrogen atoms in the chemical formula. So we started off with our pure metal, and at the end of the reaction, we've generated a new compound and a new pure element. So hydrogen was displaced from water. Another example we see is if we react sodium with water, sodium has displaced hydrogen from water, so we generate sodium hydroxide and hydrogen gas. Let's look at another example where we take calcium and we react it with water. What products would we expect if calcium displaces hydrogen? What products would we expect if calcium displaces hydrogen? What product would we observe if calcium displaces hydrogen? Calcium hydroxide, exactly right. And as hydrogen is displaced, we generate hydrogen gas. This displacement reaction is in fact a genuine redox reaction as we go from calcium 0 to calcium +2, and hydrogen goes from +1 to 0. So these hydrogen displacement reactions are genuine redox reactions. The second subclass of hydrogen displacement is when a metal reacts with an acid to give a salt and hydrogen gas. In this case, the metal is again displacing hydrogen from the chemical formula. So that in turn generates a metal chloride and hydrogen gas. So let's look at another example of hydrogen displacement. So allow me one moment to draw it out. So what would we expect the products to be if we take aluminum solid and we treat it with hydrochloric acid? What products would we expect to observe if we treat aluminum with hydrochloric acid? If aluminum is displacing hydrogen, what products would we expect to observe? Aluminum chloride, exactly right. And then we can balance this equation using normal methods. So as we can see in a displacement reaction, a pure element replaces another element in a compound to yield a new compound and a new pure element. Allow me 1 second to reload OneNote as I'm noticing a bit of delay. Okay, so the next major type of displacement reaction is the metal displacement reaction. So in the metal displacement, a metal will react with a metal salt to yield a new pure metal and a new metal salt. So in this case, the metal is displacing another metal from our chemical formula. So an example of this is aluminum reacting with iron oxide. In this case, aluminum is displacing iron from the chemical formula, and we get out aluminum oxide and iron. By the same notion, if we have magnesium solid reacting with, for example, copper chloride, the magnesium will displace the copper from our chemical equation, and in turn we get magnesium chloride aqueous and solid copper. So in a metal displacement, it's a displacement reaction where a metal is being displaced. Let's look next at a halogen displacement. A halogen displacement involves displacement of a halogen. So a nonmetal reacts with an ionic salt to generate a new pure nonmetal and a new ionic salt. So in this case, our pure element halogen is displacing the other halogen from this ionic salt. So for example, if you treat, as you observed in the lab, when you treat potassium bromide with chlorine, you generate potassium chloride and bromine. Another example, if you take a sample of sodium iodide aqueous and you treat it with bromine, what products would you expect to observe in this halogen displacement? What products would you expect to observe? Yep, sodium bromide. And our new pure element is iodine. Perfect. So displacement, we have a pure element reacting with a compound to yield a new pure element and a new compound. So we're now going to look at a tool for predicting displacement reactions. So in our activity series, quite simply, rank species in order of reactivity as a reducing agent. Now, the beautiful thing about this activity series and the beautiful thing about the activity series is you can use the activity series to predict whether a displacement reaction will occur. So the trick for the activity series is, first and foremost, step one of this process is to identify the pure element. So step one, you identify the pure element and you circle it. So let's suppose we have lithium. Step two, identify the ion or oxidized species. So let's suppose it's magnesium, just for this exercise. Now, if the arrow, you're then going to draw an arrow. So step three, you're going to draw an arrow from the element to the ion. Okay, and there are two options. So option A, if the arrow points down, then the reaction occurs. In option B, if your arrow points up, the reaction does not occur. Essentially, what the activity series is saying is that species higher on the activity series will react with species lower on the activity series. So then, based on the relative position of your pure element and your ion, you will either see a displacement reaction or you will not. And you can use the given activity series to predict whether a reaction occurs. So let's do some examples. And let's talk a little bit about the full formal guide for predicting displacement reactions. So we're going to use the reduction activity series. So elements higher and on the left of the activity series will displace cations that are lower and on the right. The neutral metal or nonmetal anion is the reducing agent, and it's always on the left of the activity series. The metal cation or the neutral nonmetal is the oxidizing agent, and it's always on the right of the activity series. If the neutral metal is higher on the activity series than the metal ion, a reaction occurs and the neutral metal displaces the metal cation. So for example, let's look at the following reaction and let's go to our activity series. So let's keep this reaction in our minds and let's find our metal. Okay, so I'm going to find my metal, in this case zinc, and I'm going to circle it. Okay. What is our metal ion in the reaction? So going back to our reaction, what is our metal ion? What is our metal ion that we're dealing with? What is our metal ion in this equation? What is our metal ion in the reactant side? Would someone like to volunteer? What is the metal ion? I'm not asking whether it's an oxidizing or reducing, just what is the identity of our metal ion? Is it zinc, copper? What is it? What is the identity of our metal ion on the left-hand side of our equation? What is the identity of the metal ion? So zinc is our pure metal. What is our ionic species? What is our metal ion in this case? Copper. Yep. Okay. So we're going to find copper. So we're going to go to our activity series table. So we have zinc circled. Okay. And we're going to find copper. Now we're going to draw an arrow. And the reason why I like this method is you can even use this method in 102 when you deal with electrochemical cells. Now my question to all of you, is zinc higher or lower than copper? Is zinc higher or lower than copper? Higher, right? So our arrow's pointing down. So then does a reaction occur? If we look at our guide, does a reaction occur? Yes, perfect. Okay. So zinc is higher than copper, so a reaction occurs. So we've established, and let's just write this down, zinc is higher than copper on the activity series. Ergo, a reaction occurs. Okay, let's look at another example. If the neutral metal is lower on the activity series, no reaction occurs. So let's look at iron and chromium. So just to reiterate, what is our metal in this case? What is our neutral metal in this case? What is our neutral metal in this case? What is our neutral metal in this reaction? Iron, okay. And what is our metal ion? What is our ion? What is our ionic species? What is our ionic species? Chromium, yep, exactly. Okay, so I'm going to go to my activity series and I'm going to find iron and chromium. Okay, I found iron. Whoops, sorry, one moment. Okay, so I'm going to go find iron and chromium. So I circle iron, I circle chromium, and then I draw my arrow. And my question to all of you is the arrow pointing up or down? Is iron higher or lower than chromium? Is iron higher or lower than chromium? Lower. So does a reaction occur? Does a reaction occur? No. Exactly right. No reaction. Iron is lower than chromium. So what I want you to do, we reviewed a lot of the major classes of chemical reactions. What I want you to do is to review this chapter one more time, practice your redox reaction balancing, and we'll continue with the last part of this chapter on Tuesday. So we may cut a few more parts out of this chapter and then move on, so that way we've covered a broad swath of material before the end of the semester. But I'll make sure that to readjust any homework assigned to reflect any parts that we're de-emphasizing. But I'd like you to practice balancing redox reactions before Tuesday, just so that way when we start seeing different types of redox reactions, you're more comfortable identifying these reactions as redox reactions, and then also using these classifications that we've discussed, classifying each of these reactions further. Practice exam 3 will be available next week, so that way you have some time to work on it. We'll do a review Tuesday of finals week, and it will be due, the exam 3 and the final will be due on Thursday, but you will have at least the week of finals week to work on it.